Hello everyone, this is section 11.1 in sequences. So what is a sequence? An infinite sequence or just a sequence is going to be a function that takes a number in the natural numbers and is going to produce a real number. So any positive natural number that I take is going to be assigned to a real number. This can be thought as a list of numbers that are written in a given definite order. So for example, A1, A2, A3, up to an. Now the number AI is called the term I of the sequence, and given that I have an, the term an plus 1 is what we're going to call the successor. So in that way, A3 is the successor of A2, A4 is the successor of A3, so on and so forth. We can write sequences in two different ways. We can write it as like between parentheses an or between parentheses an from n equals to 1 to infinity. And we're always going to assume that n starts from 1 since we're thinking in natural numbers. Okay? Now, let's see some sequences and see some examples of how they behave, specifically in terms of their different members. So if we consider an equals 1 over 2 to the n, notice that this is what we call the n term of the sequence. It's a way to define the sequence entirely by the n number. But we can find the number 1, a1. So this is going to assign 1 to the number 1 over 2 to the 1, or 1/2. A2 is essentially saying, oh, okay, so we're assigning 2, or the second member of the sequence, to 1 over 2 to the 2, right? So this is 1 over 4. A3 is assigning 3 to 1 over 2 to the 3, and so this is 1 over 8. Okay? So that's the first three members of this sequence. Of course, I can go 8 to the 4, and so now you notice this is 1 over 2 to the 4. A to the 5 is 1 over 2 to the 5. And it's very important to know these patterns, because sometimes these patterns are going to be presented to you as a set. So for example, I can give you this sequence and I can say 1/2, 1 over 4, 1 over 8, 1 over 16, 1 over 32. And I can give you this like this. And you will have to identify that an is actually going to be 1 over 2 to the n. And so that is some of the challenge that sequence presents. You need to identify the, sometimes you get the pattern and you get to identify who the members are, or backwards, sometimes you get the members, and then from the members you should be able to identify the pattern. So now let's take a look to another sequence here. So now let's go to an equals n over n plus 1. Notice that clearly the first term is going to be 1 over 2, 1 over 1 plus 1, so 1 over 2. A2 is going to be 1 over 2 plus 1, or 1 over 3. A4 is going to be 1, this is 2 over 3, sorry. And this is going to be 4 over 4 plus 1, so 4 over 5. I forgot A3, so A3 will be 3 over 3 plus 1 will be 4. And finally, A5 will be 5 over 5 plus 1, so 5 over 6. Okay, so this is one way of representing those 5 terms. Let's go to another sequence. We have now the opposite situation. We have a square root of 3, a square root of 4, a square root of 5, a square root of 6. And so notice that we're going to find what happens, what is the n number if this starts from 1. So if this is starting from 1, it means that from 1 I go to square root of 3, then from 2 I go to 4, from 3 I go to 5, or square root of 5, so whatever you want to do. From 4 you go to 6, there's a relationship between here, the initial number that I take, which is my index, and the number that I'm getting. Notice that this 1 is really accounting for A1, this 2 is A2, A3, A4 is the order of the term. So in general, I can think AN is just going to be a square root, because it clearly has a square root, of N, and then you notice from 1 goes to 3, so it should be N plus 2. Is this true? Well, when I plug N equals 1, I get the square root of 3. When I plug 2, I get the square root of 4. When I plug 3, I get the square root of 5. And when I plug 4, I do get square root of 6. So this is true. And this is assuming, of course, that this is N equals 1 onwards. Okay, so this is assuming we have AN equals N equals 1 to infinity. Of course, you could potentially say, well, I can see this as a sequence as well, Bn equals the square root of n, if I'm going from n equals 3 onwards. And that will also work, but that will not start from 1. Okay, but that will work certainly. When n is equals 3, it will be square root of 3. When n is equals 4, it will be square root of 4. So the looking for the patterns is going to depend on the initial number that you're selecting to pick as the initial. And there is a big advantage of always picking a common initial point in n equals 1. All right, so let's see one more example. Now we're going to see the first 5 terms of this sequence here. We have an equals minus 1 to the n times n plus 1 over 3 to the n. This is a more complex sequence, and this minus 1 to the n, what it does is that this transforms the sequence into something that we call an alternating sequence. So notice that when we plug in n equals 1, we're going to get minus 1 to the 1 times 2 over 3. And then in 2, we're going to get minus 1 to the 2, 2 plus 1, so 3 over 3 squared. On 3, then minus 1 to the 3, and then 3 plus 1 is 4 over 3 to the 3. And in 4, minus 1 to the 4, 4 plus 1, then 5, 3 to the 4. And the last, minus 1 to the 5, 6 over 3 to the 5. And that's the fifth term. Okay, of course, we can simplify this a bit and actually find out who those numbers are going to be. Minus 1 to the 1 is just minus 1. So this one is minus 2/3. This we can kind of cancel out probably one of the 3's, but I'm gonna leave it this way. This will be 3 over 3 squared, or 3 over 9. Let me leave it in 3 squared. Here we'll have a minus 4 over 3 to the 3. Here we have a 5 over 3 to the 4. And here we have a 6, minus 6 over 3 to the 5th. Of course, you might get right away the powers of 3 instead of having the powers stated. You might be getting the numbers, but this is one good way of representing those 5 numbers. It will get complicated going from these numbers backwards, especially if you actually have the numbers that are supposed to be. So minus 2/3, and this will be because I can cancel out this 3. This will be 1/3, and then over here I get minus 4 over 9, and here I get 5 over 81, and here essentially I'm going to get minus 2 over 81. So by simplifying a bit, so this might, if I receive this one, it might be kind of difficult to get back to the original n term. So sometimes getting the pattern is tricky than stating the first 5 terms of a given sequence. Okay, but those are some good examples of sequences. Now, in general, when we have a sequence, the sequence can be pictured by plotting the points in a graph, and you're going to see a discrete pattern. So, for example, we take the n over n plus 1. We have this number here, 1/2, 2/3, 3/4, 4/5. And we're kind of putting this here in the real line. Between 0 and 1, you see that the first one, A1, is in 1/2. Then the second one, 2/3, is over here. Then 3/4 is A3. Then 4/5 is this one here. And every time we're approaching more and more closer to 1. Okay, so you can see that we start here, but then start getting super close to 1. We can also see this here using a relationship in the Cartesian plane from n to an, and when we're graphing n versus an, you can see that the numbers are slowly approaching to 1, and 1 is like some sort of horizontal asymptote in here that is not gonna let me cross. And so this is the representation. In general, if we see this as a function, then it's going to consist of discrete points and coordinates where we have the pairs 1A1, 2A2, 3A3, and 8AN. Be careful not to confuse this with a real continuous function. This is not joined. This is just point after point after point. Now, for example, here we can see that as n over n plus 1 approaches, is going to approach 1 as n becomes large. And so because it's similar to an asymptote, then you probably are not going to be surprised that the limit when x goes to infinity of n over n plus 1 is just going to be equals to 1. And that's going to lead me to my next definition. Essentially, if a sequence an has a limit, a situation like what we just saw, we can describe that limit as L, and we can write it as limit when x goes to infinity of an is L, or an goes to L as n goes to infinity. When this happens and L is a real number, we're going to say that the sequence converges. Otherwise, if this limit does not exist or is infinity, then we're going to say that it's divergent. And so here are the example of a couple of convergent sequence. One of them is called an alternating, bouncing around between two values. It seems like a kind of sinusoidal function or wavy function that is going around the L line. And you know that as the largest value is, then we get much more closer to L. This is similarly another sequence where we see that as n gets larger, then the numbers start getting very close to L. Now, that definition has a proper technical definition. It is a sequence has a limit L if, or the limit when n goes to infinity of n is L, if for a given epsilon bigger than 0, is going to exist in n such that if the n of the sequence is bigger than that n that we pick, then the distance between the sequence number and L is going to be super small. It's going to be less than epsilon. And so what that means is that we're going to have a situation like this. After a certain end, then the sequence member are going to be between a threshold of L. They're not going to be far away from L. So it's going to be L minus epsilon, L plus epsilon, and all the points are going to be inside of that band. And that is precisely what this definition is saying about the limit. Now, in terms of divergency, if the limit of the sequence is infinite or minus infinite, or it doesn't exist, then is when we're going to say that the sequence is divergent. If an has an infinite limit, then that means that it exists number m such that if we are going past a certain number n, then the sequence is always going to be larger than that number m. And the definition for minus infinity is going to be analogous. So essentially what we're saying is let's say that we assume that is 100. 100 is my number m. So it means that after certain number of points in the sequence, so let me say 832 in the sequence, after 832, then 832 is actually going to be larger than 100. And if I pick now a number like 1,000, and so it's going to say 8100 is going to be the terms of the sequence. After 8100, 8101 is going to be larger than 1,000. When that happens, that means that the sequence is growing unbounded and is going to go to infinity. You can also see the same thing, of course, for minus infinity. It's going to be constantly larger, but in a negative sense. So these are two examples of divergent sequences. As you can notice here, we have the first case here is the infinity case, the case where it continues growing. And the other case, the case that we have here on the left side, is where it's just the limit doesn't exist because it's constantly jumping between 2 points. And it never approaches to anything. It never approaches to anything. So that's the case where the limit does not exist. The other case on the right side show cases where the limit goes to infinity. Now let's see some examples of this into play. So first, we're going to have 1 over 2n. And you can probably guess what happens here. We have limit when x goes to infinity over 1 over 2n. You see L'Hopital at this point, so you know that the below is growing much more faster than the top, and so this is going to 0. And so an equals 1 over 2n converges. Also, in a similar way, you done limits going to infinity plenty. So you know that this is going to 1. You essentially, what you do for this is you transform that limit into 1 plus 1 over n. And so this one goes to 0. And so that makes it so this goes to 1. And so n over n plus 1 converges. Okay, let me put another whiteboard. Now, for the sequence number 3, you see that this is a square root of 3, a square root of 4, square root of 5, and so you can see that the n term is going to be square root of n. But when you take the limit when x goes to infinity of a square root of n, this is just infinity. So this square root of n sequence is going to be divergent. Now, this other sequence here, an, when is minus 1 to the n plus 1 over 3n. This is much more difficult to really assess because it's kind of going between minus 1 and 1. I could say that an is going between of course, minus n plus 1 over 3 to the n, and n plus 1 over 3 to the n. So it's kind of difficult to know. But notice that in both cases, if you take the limit when it goes to infinity of minus 1 over 3 to the n, that's going to be equals to 0, which is the same at the other side. Why? Because the bottom 3 to the n grows much more faster than the top. So because these two are 0, the extreme are 0, then by a squeeze theorem, we're going to conclude that this is 0. And this is one of the theorems that we're going to see for convergency next. It's just going to be that if we can do the squeeze theorem, then we have this kind of things. All right, so last, we have this example where we have limit when x goes to infinity of 3 to the n over 2 to the n. Here the opposite is happening. This is going to infinity because the top is larger than the bottom, and so it's growing much more faster and it's going to go to infinity. So this case an equals 3 to the n over 2 to the n diverges. And the previous one, it was convergent, right? So hopefully that makes sense. All right, so this is the end of the first video. In the next video, we're going to continue seeing some criteria to find convergency of sequences.